So now we'll talk about another very interesting distribution, which is Bernoulli distribution. And this distribution is named after, I'm not sure his nationality, but it was Johann Bernoulli, right? So I guess he was Swedish, maybe. So he was a really pioneer in a lot of uh, physical and mathematical laws. So in fact, the whole family of Bernoulli, they're pretty popular in terms of their contribution in physics and mathematics. Right. So in fact, the son of Johann Bernoulli, his brother, so they all were really pioneers in mathematics and physics. Right. So a Bernoulli distribution. So to first understand what a Bernoulli distribution is, we need to understand what a Bernoulli trial is, right? So I'll give you the idea of Bernoulli trials, which is essentially an experiment which has only two possible outcomes, right? So either a success or a failure, right? Of course, these two labels, that is success and failure, they're very subjective, right? And they can be applied to any such context, okay? But a Bernoulli trial is an experiment where there are only two possible outcomes, that is a success or a failure, right? So in the case of a Bernoulli distribution, in fact, for a Bernoulli trial, the sample space will have only two possible elements, which is one S and F, right? S denotes your success and F denotes your failure. Okay, so as I already told you, the words success and failure, they are merely labels, and they do not necessarily carry with them the ordinary meanings of the words, right? So just to give an example, so for example, in life insurance, right? So a success could mean a death, okay? That is how you can define, right? So these are subjective labels, and it is dependent, or it is contingent on the user how they are going to choose the meaning of these labels, right? So in the case of Bernoulli trial, our sample space only consists of two possible outcomes. One is your S and the other is F, right? So S denotes success and F denotes failure, right? So now let's talk about the probability measure. So just try to give an example. So a very simple example of Bernoulli trial is just tossing a coin, right? So when you toss a coin, so there are only two possible outcomes, either heads or tails, right? So there are a lot of different situations in which there could be only two possible outcomes for a single experiment, and they will all be considered as a Bernoulli trial. Okay, so how do we define the probability measure for each of the possible outcomes of the sample space, or each of the elements of the sample space? So probability of S is theta. Okay, so theta is a new term that you are seeing here. Of course, in the case of tossing a coin, what is the probability of a success? So let's say I'll just give me a second. So here now we're talking about a Bernoulli distribution, right? So in the case of Bernoulli trial, right? So there are two possible outcomes, right? So one is of course your success, and another is failure, right? So this is your success, and F is your failure, right? So let's say in the case of so suppose our experiment is nothing but an experiment of tossing a coin. So you're just tossing a coin once, right? So there are two possible outcomes. One is head, or another is tail, right? So so let's define S as getting ahead. Okay, so I'll define my success as getting ahead. Okay, so that is how I'm defining S. And so in the case of tossing a coin, can you guys tell me what is the probability of S and what is the probability of F, right? Which is failure. So failure is not getting ahead. right? So probability of S is pretty simple, right? So it's 1 by 2, right? So it's pretty straightforward. So this is 0.5 and this is also 0.5. Okay, so this was just an example, but uh, if you talk about a general Bernoulli trial, so here the probability of success will be defined as theta. So theta is the parameter of this Bernoulli distribution, right? So you know that, yeah, every probability distribution, or not every, but most of the probability distributions can be parameterized, as in they have a parameter associated with them. Okay, so in the case of uniform, you saw that, yeah, k is the parameter. In the case of Bernoulli distribution, your theta is the parameter, right? And specifically, if we talk about the experiment where we're tossing a coin and our success is getting ahead, so theta will be 0.5. Okay, and you can quickly tell that the probability of f will be nothing but 1 minus theta. Why so? Because the total probability, for these two outcomes, they have to add up to 1, right? So if you know the probability of success, by default you would know the probability of f, because it will be just the remaining probability, which is 1 minus theta, right? So these are the probability measures of our uh, different outcomes of our sample space. So now we are ready to define the Bernoulli random variable. So the Bernoulli random variable x is defined as x of s is equal to 1, x of f is equal to 0, right? So if you think about the notation that we have been following, right? So let's say this is f, this is s and f, and this is, let's say, 0, this is 1, right? So now you can see x of s is equal to 1, right? So x of s is 1 and x of, right? So this is the mapping given by x. So x is our Bernoulli random variable, and x of s is 1 and x of f is 0, right? So this is how we are defining our random variable, right? So x is essentially defined as the number of successes that occur, right? So when you're tossing a coin and you define the success as getting ahead, so when you toss a single coin, right, so I can either you can get a head or a tail, right? So that is what's the definition of this random variable, right? So x of s is equal to 1, x of f is equal to 0, right? So these are the two possible values which our random variable can take, that is 0 and 1. Okay, so there's one thing I wanted to tell you guys, right? So if you talk about Bernoulli random variable, right, so this can also be written in this fashion, and in fact I would suggest you guys to uh, if you want to even remember, right, so always remember in this particular format, but you can also learn in this particular format as well, right? So these are essentially the same thing, and I'll just show you how, right? So here also Bernoulli distribution. So probability of x is equal to x. Now we would need to define the probabilities for by a Bernoulli distribution, right? So simply said, it is defined as theta 1 minus theta if x is equal to 1, or here if x is equal to 0, right? So this is how we define the Bernoulli distribution, right? And let's write this formula as well, and we'll see that, yeah, these are essentially the same thing. So theta to the power x, 1 minus theta to the power 1 minus x. Okay, so right, so this is what we have, right? And x can of course take only two possible values, right? So when I'm writing curly braces, you know that our set only contains these two specific values, right? So I've explained this concept in the last class, so I hope that should not be a problem. So let's plug x as 0. So if I put x as 0, so theta to the power 0, 1 minus theta, 1 minus 0, so this is essentially 1 times 1 minus theta. Okay, or I can simply say 1 minus theta if x is 0, right? So this is for x is equal to 0. Now if x is equal to 1, what will have? Theta 1 minus theta 1 minus 1. So this will be theta multiplied by 1 minus theta to the power 0. So this term will be 1. So it will be theta, right? So this is if x is equal to 1. So essentially, this is the same thing what we have written here, right? So this is the same thing what we have written here, right? So the probability distribution or probability distribution for a Bernoulli distribution can be written in this particular way, right? So theta is a probability of getting a success, right? So theta is getting a probability of getting a success, and of course your random variable x is defined as the number of successes, so they can be either 0 or 1. Okay, so now we know this particular distribution. Okay, so I want you guys to tell me, so what will be expectation of x? Okay, so this is pretty straightforward to calculate. So let's say this can be, so x can be 0. So 0 into probability of x is equal to 0. In fact, plus, right? 1 into probability of x is equal to 1. So this will be 0 plus 1 into theta, which is nothing but theta. Right? So this is the expected value of this Bernoulli random variable, right? And this is really important. So of course, when you're doing a coin toss, so what is the expected? And you define your random variable as the number of success. Okay, so of course that can be 0 or 1. So what is your expected value of that random variable? So that is theta, and in the case of coin toss, that is going to be 0.5. Okay, so that is how we define the expectation of a Bernoulli random variable. And needless to say that you can also calculate the sigma squared as in the variance. So variance is again pretty easy. So variance of x is nothing but expectation of x squared minus expectation of x whole squared. And I'm not sure if I'll get space here, but I'll just write above. So expectation of x squared, because the first term will not contribute, so that is going to be 0. So from the second term, we're going to get theta squared, right? So sorry, it's going to be 1 squared into theta minus theta squared, right? So theta into 1 minus theta, right? So this is what we are going to get, right? When we calculate the expected value or the variance of this Bernoulli random variable, right? So this is the overall concept of Bernoulli distribution. A Bernoulli distribution is applicable to any such phenomena or process where we're only dealing with only two possible outcomes, and that experiment is only conducted once. Okay, so right, so this is how Bernoulli distribution works. Okay, now you have been seeing moments. Okay, right, so you're not actually sure how the moment is defined. So moments are essentially an alternative to your probability distribution functions in a way, not precisely, but I'll just try to give you an idea. So uh, so if you talk about moments, in fact, they are moment generating functions. So they are essentially written as e to the power tx, right? And if you know the expansion of this, so 1 factorial plus tx whole squared by 2 factorial, something like this. So and if you calculate the expectation of this, so expectation of 1 is 1 plus expectation of this t times expectation of x plus let's say t times expectation of x squared, something like this, 2 factorial like this, right? So this is defined as the first moment, right? So which is essentially coincident with the mean, right? So first moment is the mean. This is called the second moment, second moment, and as you can see, this is not exactly the variance, but we'll need the second moment to find out the variance, right? And then there are of course higher moments like third moment, fourth moment. So there are statistics such as so you know statistics such as mean and variance, right? But there are certain statistics such as, let's say, kurtosis, skewness, right? So you know about left skewed or right skewed distribution, right? So we can actually calculate this metric for any distribution and see if this distribution is actually skewed, negatively skewed or positively skewed, right? So this comes from the first moment, this comes from the second moment, this comes from the uh, third moment, most probably. I'm not sure, they could be interchanged, but I'll just have to check, right? But this is how we can calculate different statistics which actually define the shape of your distribution, right? So if I show you a simple, let's say, I'm not sure if you remember the normal distribution from earlier. One second. Okay, so if you remember the normal distribution, so mean and the variance. So variance will tell you how spread out your so higher the variance, so the more the spread out your probability distribution would be, right? And how peakedness, right? So there could be one distribution such that something like this, right? So this changes the shape of the distribution, and this will be governed by the kurtosis, which will tell you how what's the peakedness of the distribution. And then of course you have the skewness. So for skewness you can have something like uh, some distribution like this or some distribution like this, right? So it's negatively skewed or positively skewed. So these are different statistics, or in fact different metrics or quantities which actually can tell you the nature of the distribution, right? So skewness is the third. Okay, thanks for correcting. So skewness is the third. Okay. No, so Sanchita is asking, is this related to the physics moment of a quantity? uh, Not exactly. um, I actually don't want to comment on that, because it can get confusing for most of the guys who might have forgotten a lot of mathematics from the 11th and 12th. But just think of moments, or moment generating function, which is e to the power tx, which gives you different statistics, and those statistics can actually tell you the shape of the distribution, right? So mean tells you where the expected value of the distribution lies. Variance tells you the spread of the distribution, right? Kurtosis tells you the peakedness of the distribution. Skewness tells whether it's negatively or positively skewed, right? So these statistics, all these statistics, uh, they come from the moment generating function, and they define, or they define the characteristics of your the shape of the probability distribution. Okay, so this is what I just wanted to digress a bit and tell you about the moments. So as you can see, so mean is the first order moment, and your variance is not actually the second order moment, but to calibrate the variance you need the second order moment. Okay, so that's the thing. Okay, so I think, yeah, we can move ahead. So in the case of Bernoulli distribution, right? So let's take an example of a simple coin toss, right? So we define our random variable as the number of heads when we toss a coin, right? And of course, you know that this random variable can only take two values, 0 or 1. So because you're doing a single coin toss, so it can take value either 0 or 1. And the parameter of this Bernoulli distribution, which is theta, that is the probability of success. So probability of success is getting ahead, and so that will be 1/2. Okay, So you can write your probability distribution as this, right? So half for both of these, and mean you can calculate 0 into 1 by 2 plus 1 into 1 by 2, that is again 1 by 2, that is equal to theta, and we have already calculated this, right? And variance will be theta times 1 minus theta, that will give you 1 by 4, right? So what does the mean tell you in the case of this particular Bernoulli distribution? So it tells you when you define your random variable as the number of heads when we toss a coin. So it tells you that, yeah, when you toss a single coin, you'll get a 0.5 number of heads, right? That is not a very good way to say things, but essentially the number of heads can be 0 and 1, but the expected value might not be equal to those specific set of values, but it can be somewhere between those, right? And in this case, we're seeing that it is half, right? So then when you toss a coin, what is the expected value of a head, of getting a head? So that is half, right? So the expected number of heads will be half, and the variance will can calculate, that is 1 by 4, that is 0.25. Okay, so variance essentially tells you how far your values are from the mean. Okay, so that is what variance captures, right? So this is all about the Bernoulli distribution, right? So it's essentially this distribution stems from a very basic experiment, which is what we'll call as a Bernoulli trial. And a Bernoulli trial only deals with two possible outcomes, right? Either a success or a failure, and do not go by the dictionary meaning of success and failure, but they are these labels are subjective, and you can define as and when you want. Okay, so this is essentially Bernoulli distribution. So can I get a hell yes if you're able to understand Bernoulli distribution? Okay. 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 So I want you guys, so Sheets is asking, can you take more examples? Of course, there are a lot of other examples. So for example, if you talk about insurance, let's say if a single person will get an insurance or not, and that you can label as 0 and 1. Okay, so that again is a Bernoulli trial in a way. Okay. So firstly, before we can discuss the binomial distribution, we'll talk about the sequence of Bernoulli trials. Okay, so let's consider a sequence of n Bernoulli trials as above. So we saw an example of a Bernoulli trial which has two possible outcomes associated with it, right? So so let's consider a sequence of n Bernoulli trials, n such trials in which for each of these trials we have only two possible outcomes, either a success or a failure, right? So consider the sequence of n Bernoulli trials. So the first thing is, or the first condition for such a sequence is, the trials are independent of one another, right? That is, the outcome of any trial does not depend on the outcome of any other trials, right? So let's say if you tossed a coin, right? So that is a single Bernoulli trial, right? Then you can toss that coin again, right? And you define, let's say, so you can define your success as getting ahead, right? So when you toss a coin, right? Or if you toss a coin for the second time, right? So the outcome is not dependent on the previous trial or the previous experiment, right? So the trials are independent of one another in the simple example of tossing a coin, right? So trials are independent of one another. So whenever we are considering a sequence of n Bernoulli trials, so there we are in fact assuming that these trials are independent of one another. Okay, so just an example, which is tossing a coin, right? The second is trials are identical. That is, the probability of success is not getting changed. Okay, so in this case, we'll not consider these, let's say, trials in which we are drawing the aces. So these will not be considered as Bernoulli trials, because this condition, which is probability of S is equal to theta, that is not remaining the same. Okay, so for the first success, or the first for the event when I drew an ace, so the probability was 1 by 13, and out of the remaining my cards, my probability is getting changed, right? So probabilities are getting distorted, so the trials are not identical in a way. Okay, so in this particular example, so that will not be considered as a Bernoulli trial, or a sequence of Bernoulli trial in which, let's say, you are drawing the aces in sequence. Okay, so but this simple example of tossing a coin, right, and doing such tosses for, let's say, n times, so that will be considered as a sequence of n Bernoulli trials. Okay, so there are very two important concepts here. The trials should be independent of one another, right? So the outcome of any trial does not depend on the outcome of any other trial. So in the case of ace, why that is not a Bernoulli trial? So the or in fact the sequence of n Bernoulli trials. So there, what we are seeing, that once I draw an ace, so it automatically affects the outcome of getting an ace on the next trials. Okay, so and the trials are not identical, as in my probability of success or probability of getting an ace, that is not the same, right? So these two conditions have to be let's say satisfied for what we can call as sequence of n independent identical Bernoulli trials. Okay, so if these two conditions are satisfied for any sequence of n Bernoulli trials, we'll call such a sequence as sequence of n independent identical Bernoulli trials. Okay, and they're also called as independent and identically distributed, or in short we'll call them IID, right? So IID, this is a very popular acronym used across probability and statistics, so I think you should get used to this particular term, right? So if we have any such sequence of n independent identical Bernoulli trials, we'll also call them an IID. Okay, that is, they're independent and identically distributed. So now we know what is the sequence of a Bernoulli trial. So let's understand what a binomial distribution is, right? So this is what Sheets basically was concerned about, right? So I'll tell you how it differs from your normal Bernoulli trial, right? So a Bernoulli trial is essentially any experiment or a single experiment in which there are two possible outcomes, right? In binomial as well, for a single trial will have two outcomes, but there could be n such trials, right? So in Bernoulli trials, in Bernoulli distribution, we are only concerned with one Bernoulli trial, right? But in binomial distribution, we can have n such Bernoulli trials. Okay, so let me try to cover this in detail. So in the case of binomial distribution, I will define the sample space as the joint set of outcomes of all n trials. Okay, so the joint set of outcomes of all n trials. Okay, so let's say you are doing 10 tosses of a coin. Okay, so firstly you can get head, tail, tail, head, etc. Right? So that is the joint set of outcomes of all n trials. Okay, so the probability measure is essentially defined as the same, right? So probability of S is equal to theta only, right? Because for each trial, the probability of S will be equal to theta. So theta again is the same parameter for the binomial distribution, right? So you know that a particular probability distribution is parameterized using a parameter. So in the case of Bernoulli distribution, we had that parameter theta, that was the probability of success. Here also, in the case of binomial distribution, we'll have the same probability measure as in theta, which will be probability of success, right? So now a very important thing, right? So in the case of binomial distribution, our random variable x, it is defined as the number of successes that occur in the n trials. Okay, so it is defined as the number of successes that occur in the n trials, right? So this distribution is in fact defined as probability of capital X is equal to small x, and this is defined as ncx theta to the power x 1 minus theta to the power n minus x. Okay, so let me just write this in the frame here, right? So probability of x is equal to x, right? So this is ncx theta to the power x, and what do we have? 1 minus theta to the power n minus x, right? And x, what are the set of values which x can take? So it will be, because there are n trials, so it will be x can take these values, so 0, 1, 2 till n. Okay, and of course your theta lies between 0 and 1 because it's the probability of a single success, so that will be between 0 and 1 only, right? So now if you plug n as 1, right, because in the case of Bernoulli trial, we're only doing a single trial, right? So if you put n here as 1, so 1 cx theta to the power x, 1 minus theta, 1 minus x, right? So this term, because x can take only values 0 and 1, right? So for both of this case, this will be 1. So this will be essentially theta to the power x, 1 minus theta to the power 1 minus x. This is the same probability distribution which we have seen for the Bernoulli distribution, right? So this is the same thing. So essentially what you can think of, that Bernoulli distribution is a very special case of binomial distribution where the number of trials is 1. Okay, so I hope that would answer your question. So let's go look at some visualizations, and that will really help you understand what's going on. Okay, so I'll first talk about the Bernoulli distribution. So of course, you know, in Bernoulli distribution we have one parameter which is p, that is theta, right? So okay, so let's say you're doing a simple tossing of a coin, right? So your theta or p is essentially 0.5, right? So you can see the probability distribution for 0, this value is 0.5, and this value is again 0.5, right, for 0 and 1. Okay, and let's say if the coin was not fair, it was a biased coin, and suppose it was biased towards, let's say, a particular value, let's say towards 1. So as you can see here, maybe I can, let's pick a nice number like 0.8, right? So here 0.8 is the probability of getting 1, and or so 1 you are essentially defining as, let's say, getting ahead. Okay, and 0 is you are defining as 0.2. Okay, so this is how the probability distribution can look like, but in the case of, let's say, a fair coin, will have the probability as 0.5. Okay, and so if you move this slider, so you can also see the so this is the normal PMF, which is the probability mass function or probability distribution function. But if you move the slider, you will be able to see the cumulative probability, CDF, in fact. Okay, so less than 0 is of course 0 cumulative probability. When it's at 0, the cumulative probability, it climbs up to 0.5. It remains at 0.5 between all the possible values between 0 and 1, and of course there are no such value between 0 and 1, right? So as you can see, and when it's 1, the cumulative probability is getting 1, and of course, as you can see, for all the values after it, it will be 1 only. Okay, so this is how we can visualize a simple Bernoulli random variable and its probability distribution, right? So this is the cumulative or CDF, right? And this is, in fact, right, so I'll just move the slider here, and this is the PDF of the Bernoulli distribution, right? You can move play around with p, and you can see how the distribution is changing. So now for p is equal to 0.3, you can see how the probability cumulative or CDF looks like, right? So you can experiment. And now here for Bernoulli, in fact, we can now change to binomial. Okay, before I discuss this, okay, so from here you can see that expected value will be simply 0.5, right? So right, and now let's move to binomial, right? So in binomial you have this formula, right? So let's say I'm doing 10 trials. Okay, I'm doing 10 trials, and I am doing a simple coin toss only, right, in each of these trials, right? So my p is 0.5 because for each of the trial and my success is getting ahead, and that will have the probability 0.5. Okay, so the probability of success and failure for a fair coin is the same, right? So as you can see, in fact I can, right, so as you can see from here, so okay, so I think, yeah, you guys can work with so maybe I'll just reduce the number of trials for better visibility. So let's keep it to 6. Okay, so let's keep this to 6. Okay, now I can reduce this a bit. Okay, so now as you can see, so which so my random variable in the case of binomial distribution is the number of successes that occur in the n trials. Okay, so let's say if I do 6 tosses of a coin in sequence, right? So I toss the coin once, I toss it again, right? So my random variable is defined as the number of successes. Okay, so now let's define what success is. So let's go by my preference. So I'll define success as getting ahead. Okay, so how many heads I'm getting in these 6 trials. Okay, so so in these 6 trials, as you can see, it's you can already guess that you'll so you are most likely to get 3 heads. Okay, so when you're doing 6 trials, so your random variable value, which is 3, so this is the most likely value, because when you're doing 6 tosses, so there you'll have 3 heads likely, right? So that's the most likely. And what are the least likely scenarios? So let's say getting 6 heads or getting 0 heads in 6 coin tosses, right? So these values are very least likely. And let's say getting only 1 head and 5 tails, so that is also least likely. But getting 3 heads, that is the most likely, right? So this is the probability distribution of a binomial distribution in which we have 6 trials and we're doing a simple, let's say, coin toss, right? And I have kept P as 0.5, right? So right, so I'm assuming that the coin is fair. Okay, and now if we drag the slider, so you can see how the CDF looks like. Okay, so if I go at 6, it will be constant, right? So it gets saturated after this, right? So you can check for all the values, right? So you can check, so this gets saturated, right? Because the cumulative probability will be 1, right? After 6, right? So you can see a very small minuscule jump here. So you can see a very minuscule jump when I go to 6, right? So as you can see here, very minuscule jump, right? Because a probability of getting 6 heads in 6 coin tosses, that's a very unlikely, right? That's why the probability is pretty low, right? So, and now you can also play around with P. So suppose you have a biased coin, it's not a fair coin. So let's say it's skew or biased towards a head, right? So I'll just, yeah, move the slider here. So let's say if the probability of getting a head is 0.8, so you can expect that in 6 coin tosses, I'll most likely get 5 heads, right? So as you can see, so it's getting shifted towards the right, right? So we can call this a which distribution? Negatively skewed distribution, right? So so this is what Bernoulli distribution, binomial distribution is, right? So you can play around with P. Let's say my probability of success or probability of getting ahead is pretty low, that is 0.2. So as you can see, so in 6 coin tosses, it's less likely that I'll be getting a large number of heads, as in 5 or 6. So mostly I'll be getting either 0 heads or 1 or single head or 2 heads, etc. Right? So, and you can of course play around with n, which is the number of trials, and these things will become pretty clear. Okay, so this is more or less about the binomial distribution. And let's see how can we calculate the mean and the variance for the binomial distribution. Okay, so in this case, expectation of x is nothing, because this is a discrete distribution, so we'll use the sigma, not the integral. So this will be x multiplied by ncx theta x 1 minus theta to the power n minus x, right? And this x will take value from 1 till n, right? I don't want to go into the details of the calculation, but if you people are aware how this can be calculated, so this will be a pretty trivial task. So maybe let's try to see if this actually makes sense. So here we are seeing that mu is equal to n theta. So suppose if I take n as 3, okay, so my expectation should be 3 theta. Okay, so let's see if I actually get that. So first term will be 1 into nc1 theta 1 minus theta, so n is 3, so it will be squared, plus 2 into nc2 theta squared 1 minus theta 1, plus 3 into n, and so n is essentially 3 here, of course. I'll just, yeah, so this is 3 only, so 3c3 theta 3 1 minus theta to the power 0, right? So if you can add this, I'm not sure if this will come out to, so this is 3 theta minus theta square plus, so 3c2 is again 3 factorial divided by 2 factorial into 1 factorial, so that will be 3 again. So theta square 1 minus theta plus 3 into theta cube, right? So if you calculate this, I'm pretty sure you're going to get 3 theta. Okay, so this is the expectation of the binomial random variable, right? So mu is essentially n times theta, right? So, and this also makes sense, right? So because what is mu? It is the expected value of a random variable, and our random variable is the number of successes that occur in the n trials. Okay, so let's say if you do 6 coin tosses, okay, and theta is 0.5, okay, so your mu will be 6 into 0.5, that is 3. So you're saying that I'll be getting 3 heads when I do 6 trials, right? So it makes sense, right? So that is how you interpret the mean, and the variance will again can be calculated. So it will be n theta times 1 minus theta, right? So if we know the addition, let's say in the general notation of n, if you can do this summation, so you'll be able to arrive at these two values, right? But you can do this particular calculation, let's say in Wolfram or right, or anywhere in any mathematics calculator, and you can find these formulas. Or maybe you can be a bit curious and try to do the on your own, but eventually you'll come at these formula only, right? So here we have 2 parameters for a binomial distribution. One is n and the other is theta, right? In Bernoulli trial or Bernoulli distribution, we just had 1 parameter, that was theta, right? But in the case of binomial distribution, we need to specify 2 parameters, right? So it's a bi-parameter distribution in which we not only need to specify the theta, that is the probability of single success, but also the number of trials that we want to do, right? So essentially, binomial distribution is in a way a sequence of let's say n Bernoulli trials, okay? And you can expect, so I want you guys to tell me why are we having NCX here. So maybe I'll just clear the Padlet and then you guys can answer. So can you tell me why are we having NCX in the probability distribution? So what's your best guess? So you guys can start answering on the Padlet. So, okay. I think you guys can try, right? So what's our definition, right? So essentially we need to have X successes in n trials, right? So we are selecting X successes from n trials, okay? and we are not bothered actually about in which order we get these successes, right? So let's say if I am doing 6 coin tosses, I am saying that I don't want let's say first 3 heads or last 3 heads. I want total of 3 heads, right? So the first head can come, let's say, in the first coin toss, and the last two and the remaining two can come in the, let's say, the fifth and the sixth, right? So I'm not actually bothered about the order in which my heads are coming, but it's just that I want to get at least those successes out of those end trials, right? So that's why we are having this combinatorial, which is NCX. Okay. So are you guys now comfortable with the concept of binomial distribution? Can I please get a yes from you guys? If you are able to understand what's the difference between a Bernoulli distribution and a binomial distribution, right? So each of the trials in your binomial distribution is a Bernoulli trial. Okay, so that is what we have learned, right? Okay, perfect, guys. So I think, yeah, we can move ahead. So for binomial distribution, you can again, let's say you're doing a coin toss 6 times. So you can calculate the probability of X according to this particular formula, right? Or this particular formula, right? You can calculate by plugging each value of X. So X can take value 0, 1, 2, 3, 4, 4, 5, 6, right? So, so yeah. So you can calculate all those values and okay. I think in my formula, I think X will be 0. It will start from 0 because we can get 0 heads, right? So there's no success at all. Okay. So you can calculate the probability distribution in this way, just by plugging the value of X and calculate that particular weird looking term. And then you can calculate the mean as simply n times theta, which is 6 times half, and variance is n theta into 1 minus theta. And as you can see here, the probability here is the highest, right? And it's the least on the edges. And in this case, you can see this is a perfectly symmetric distribution, right? So getting one, so probability of getting 1 head or 5 heads, so it's the same. Probability of getting 2 heads or 4 heads, it's the same. Probability of getting 0 heads or 6 heads, they are the same. And probability of getting 3 heads is, of course, the highest. Okay, so this is what the binomial distribution is.